From the previous video, we have concluded that the Q potential ln of sum over Rs exponential minus alpha n minus beta Es is equal to PV by KT. Okay, so that was our conclusion. So I told you about the relevance of this expression also. Now to continue the discussion, let's introduce a quantity Z, okay, small z, is equal to e raised to minus alpha. Alpha is minus mu by kt, therefore I can tell that this is e raised to mu by kt. And this term we call as the fugacity. This Z is otherwise called the fugacity. So what is fugacity? So fugacity is a measure of the gas to expand or escape. So this basically tells us the capability for a gas to escape or expand. Okay, so basically it's some kind of a pressure value, right? It's a pressure value needed at a particular or a given temperature to make a non-ideal gas obey the rules of an ideal gas. So that is another way in which one defines a fugacity. So basically fugacity is Z is equal to e raised to minus alpha equal to e raised to mu by kt, and you know what does the mu and all those mu, k and t means by. So it's a measure of a gas to escape or expand, and also in addition it can be defined as a pressure value needed at a given temperature for a gas to obey the rules of a gas. Means a non-ideal gas, the normal gas, right? Obey the rules of ideal gas, right? So the question would be, if a gas is ideal gas, for example, what will be its fugacity? So in that case, the fugacity and the pressure are same. For an ideal gas, fugacity is equal to pressure. Okay, so this is the concept of fugacity. Now utilizing this concept of fugacity, we will try to simplify our expression for Q potential, or manage with the Q potential expression. So let's do that. So therefore I can write now the Q as equal to ln Q potential, here Q potential ln sum over Rs Z raised to nr e raised to minus beta Es, right? This is equal to ln sum over Rs, or we will do the summation with respect to n. sum over nr equal to 0 to infinity z raised to nr q and bt. What is q and bt? So q and bt was our partition function for the canonical ensemble. You remember that, right? Right. So that is Qn. So therefore I can write as a modification a new kind of partition function, which is ln theta z vt. ln theta z vt. So in your textbook, okay, in your textbook it is not actually in your Patria. Actually, it is not theta. Actually, it is script q. But it's confusing to write for me. That's why I preferably put theta. So one can always use the script q for representing this partition function. So what is theta zvt? So let's see, sum over nr equal to 0 to infinity z raised to nr q and vt. So and this theta is, as I told you, this is the gram canonical partition function. And you know what does a partition function means by what is the significance of a partition function, and all those significance and statements do apply over here also. I'm not repeating into that. You can go back to your similar portion in the partition in the canonical ensemble and make yourself reminded. Okay. Now, which means that we know that Q is equal to PV by KT, right? So therefore here also I can write PV by KT is equal to ln of theta z vt. So this is another thing which we should be noting down. So that is it. So we have basically introduced one of the very fundamental things, which is the gram canonical partition function in our situations. So in the next video, we will try to do one of the examples. We have done various examples in the case of canonical ensembles, but here we will do one example which is of an ideal gas in the next video.